so we have 2 more talks before lunch. So this next speaker, I want to introduce, you didn't want to theatrically.
Oh, sorry.
You want to go down and then theatrically, yeah. So another story from a couple of years ago. So I'm sure a lot of you guys know Ampower as well as EEV blog. Personally, I grew up on Bob Pease videos, and that's kind of what got me really in electronics. And then then I've been working on software for a long time, and then finally I got back into hardware with supply frame, and I was trying to figure out, well, what's the thing out there that's kind of brings that old spirit of like Bob Pease and Weidler and all the crazy analog guys from back in the day. And then I discovered Dave Jones, and it's like, oh my God, like this guy's awesome. And then I discovered the Ampower. So I was, and then I got a lot of people in the company hooked on the Ampower, and we were listening, and we were all like big fans. And then I think it was, at some point, it was like Saturday night, and my CEO calls me, and he tells me, hey, you know what? Chris Gammell just announced on the Ampower that he's leaving his full-time job. And for us, Chris was like, someone that we listen to every Monday as we go to work. And Flag was like, we should call him and see if he wants to join us. And next week he showed up, looking ridiculously, by the way, with a Google Glass, because apparently that was a thing. So he showed up with a Google Glass, and so I reserved the right to tease him about it. But she joined Supply Frame working on a bunch of different products. But he's also working on us on a lot of other crazy things, and still running the Ampower, and still just tries to change the world of education and all the other idealistic stuff that he's doing. But he's an amazing guy, and I'm really honored for the last 2 years having a pleasure to work with him. So I think as we all grow up, we eventually get to work with our heroes. He's not my hero anymore, he's just a buddy. But so yes, ladies and gentlemen, Chris Gammell.
Thanks, buddy. All right. Thank you, Alec, and thanks for not building me up too much there. That was really great. So yeah, I run the Ampower with Dave, but more importantly, I'm a member of Supply Frame. I work on sites like Parts.io and Find Chips, and a new one, Supply Effects, I'll talk a little bit about later. But I also do education stuff. I'm really interested in helping people along their education journey, because I remember how it was getting started and trying to figure out where do you actually start, how do you actually get started, what are the next steps, and it's tough, right? I mean, so I've done surveys before too, where I ask people, well, what are the things that you're having trouble with? And people always talk about, well, connecting theory and practice. Those are the things that I really need some help with, and maybe you identify with this as well. Right, and so when you see, theory and practice are a huge piece of electronics, but it's always that crossover piece in the middle that is the hard part. So I started looking at it and started thinking about, well, what do these two things represent? So for theory, that really is like bottom-up, that's bottom-up learning, right? So that's Circuits 101, you walk into class, you are presented with a bunch of equations, you have first principles, you start talking about physics, and it's tough. If you've been through that, you probably know that. If you're on the practice side, you're starting with kits, you're starting with building stuff, and you might have less understanding about the underlying things going on, but you can start to see more stuff here. When you want that middle piece, my assertion is that even for that middle piece, it's still going to be top-down learning that actually is a best-case scenario, and that's what I'm going to try and talk about here today. So let's start with an example of bottom-up. This is what bottom-up feels like to me. When you start talking about bottom-up learning, this is what it feels like, right? You just have a wall of equations, and your first response is that, right? You're just frustrated. Sometimes people start seeing the math, and you run into the math, and you just fall off the map right away, right? You don't even know what step to take next. So let's do this little survey here. And actually, I was thinking about it. We have an extra added thing. Everybody turn your badge on. That will be easier for me to see it. You turn the lights on for the badge. It's cool seeing it all light up. Okay, so hold up your badge if you have ever worked on an electronics project before. Okay, wow, great. Hold up your badge if you've worked on one in the last year. Okay. Last month, the last week, Nice. Okay, this is what I'd expect from the Hackaday crowd. This is good. A lot of people work on electronics regularly. But there are people that are at the beginning as well. There were some people that didn't have the badge up at all. And a lot of this talking about top-down learning, it's relevant to the people that are starting out, but it's also relevant to people that are kind of just trying to advance further on into their electronics journey. So let's do a little exercise here. And one more time, you can, if you don't have your badge on still, it's okay. Hold up your hand if you've ever designed a car. Really? One? Oh, wow. Small car, small car. Okay, yeah. I'm talking about a big car. Designed a car. Has anyone designed a car? So we're gonna do a little simulation here. This is what bottom-up electronics feels like if you're designing a car. So what's the first step when you're designing a car? You learn thermodynamics. Right? That's the first step. If you're doing bottom-up, you would learn thermodynamics first because, of course, thermodynamics govern all of the explosions that are happening in the pistons and driving stuff around. And that is what bottom-up learning looks like. You start from these first principles, and then eventually, way down the line, you build a car. I don't want to design like that. I want to go the other direction, right? So we're going to design a car, just real simple. So what should a car have? 4 doors, 4 wheels. We're going to say a sedan-sized body. Gas engine, and then I just said internals kit. You're going to see very quickly I have no idea about cars. So we're just designing for the, just a general idea here. But an internals kit, right? So let's also assume, let's suspend some disbelief and say that you can buy all these parts individually at the car store. I don't know if this is actually a thing, but someone should start this car store. So what we're going to do is we're going to assemble this car from the top level, right? So we're doing this top-down kind of thing. While we're doing that, what do we have? What do we find out? Well, we find out that we have built a thing. We have built a finished good, right? And in that process, we've learned some of the difficulties of, oh, well, the wheels didn't go on right, or we learned that we were missing a back seat or anything like that. But the idea is that the iteration is the most important part, right? So that first thing is just getting that first car out is the really important piece because that's going to ultimately then inform the rest of your design. So let's take it back to electronics because, again, cars I have no idea with. Let's pretend that now one of the things we figured out is that this car kit, this internal kit, did not come with a dome light, right? So you're trying to read a book in your car in the parking lot, and you can't read it because there was no light in that first iteration of the prototype. So now what we're going to do is, we're basically diving down in the layers of abstraction, right? Internals of the car is the big thing. The light is one component of that. Now we're just going to take that internal light as an individual component, and we're going to design that light. Great. So we got a block diagram. Great. So we know we want maybe 5 LEDs to light up the internals of that car. Each one has a 3-volt drop. But now we already see some of the constraints of that top level problem informing the other stuff, right? We know we're in a car, so we're going to have a 12-volt battery. Great. Well, that also means that now we need a switcher to go from 12 volts up to 15 volts to power all those LEDs. So we need a switcher. So let's design this system right here. Ready? 1, 2, 3, done. Right? And this is the first step of any design. It's using existing modules to solve your problem. Now we have a single iteration done. We have one module and we start assembling it, right? So we basically have, maybe we use the CNC machines back there and we start assembling a prototype and we have this module in here and that is our first iteration. Now that first iteration also informs what we're going to do next, right? So the next thing, maybe we have a new design requirement. So that module was too bulky. That module was too expensive. It didn't handle heat well. So what we're going to do is we're going to dive down into the layer of abstraction, next layer of abstraction down, and we're going to design our own module, right? And the key point here, to tie it back to the learning piece, so far you've needed to know very little about electronics, and yet you've still designed a thing. Now we're going to redesign that thing, we're going to iterate on it, we're going to redesign the thing, and now we start running into, okay, now we have to actually learn new things, right? So we need to understand the boost regulator here. We need to understand some of those equations. We need to start plugging in values using app notes. We need to start understanding how to pick capacitors and inductors and some of these other things. But the key point is that we didn't need to do that from the beginning. We didn't start from physics. We didn't start from V equals L didt, right? We started from, I need a thing. Let's design each next layer of thing, and we're going to learn things along the way. Now, this can keep going, right? You can keep going down the layers of abstraction here, right? So now we say, well, that LM3578 isn't the right thing, so we're going to take the circuit that they give in the app note, we're going to just redesign it here, because maybe we need different turn-off time, right? We need to turn it off really quickly for whatever reason. We've learned this in our prototyping, and now we can start to optimize for that. Again, you can do that for cost, you can do it for speed, you can do it for anything in there, but the idea is that you start with a finished piece and then you redesign it, and you dive down in the layers of abstraction. Now you're going to be learning other new things. You're going to be learning about maybe Miller capacitance. You're going to be learning about high-speed circuits, high-speed layout, things that you need to learn as you encounter these new problems. And if you're really crazy, you could take it all the way to the extreme. You could get it all the way down to the silicon level. If you really wanted to, you could go and learn silicon processing, and you could learn how to design chips from scratch. I don't recommend it, but you could learn all that stuff, and you can optimize your system even more, again, starting from that first module all the way down, and each time you're going to have to learn new things. I still think this is the best way to do it. So we had multiple versions of this with all of these products, the exact same thing, but we basically took what we've learned with each iteration, and then we've dove down to the next abstraction layer down, and then we've needed to learn new things. Like I said, things like Miller capacitance or high-speed design, stuff like that. So why do we start here, right? This is Ohm's law. I have been accused of being a very big fan of Ohm's law, and I still am today. So why don't I say you should start here? Because this is, Circuits 101, this is where you start, right? Everybody's started with this one before. The reason is because it gives you tunnel vision. That's the main thing, is that it gives you tunnel vision because when you start with applying equations to everything, you believe that everything needs an equation. And I don't think that's actually true. So let's talk about how a lot of people get started. You have an LED, you have a resistor, you're trying to get it working, right? You put it together, you put a 5-volt source on it, and nothing happens. Now, I don't know about you, but one of my first steps back in the day would have been, looking at a textbook or going to Wikipedia, basically diving down the rabbit hole. And that is actually a very dangerous thing. That's something that I see a lot with the students I work with and people trying to learn electronics is they go to Wikipedia and they look at an equation, and then the equation leads to another page. And the equation leads to another page. And by the end, you're 4 hours later, you're sweating, you're super confused, and you still don't understand anything more. Even if you maybe encountered the right equation along the way, you still haven't gotten to where you need. So what is the solution to this? It's not jumping down the rabbit hole, it's actually going up, right? It's going up a layer of abstraction. So in this case, you have an LED, you have a resistor, you don't understand. What should you do next? I was talking to Mike Harrison about this, and he'll be talking about similar kind of stuff too. Dave, my co-host, he loves talking about this too. You take things apart. Right? That is how you start to get your arms around these different problems. So you have an LED, you have a resistor, you don't understand why it's not working. You don't go and look at an equation. What you do is you go look at things that have an LED. You take something like this that has an LED on it, and you take it apart, and you take a look at it. Take something else apart, take a look at what's going on in there. Right? You take a look at all the different schematics that might be out there, and you start to look at that. And what you're ultimately doing is you're pattern matching. You're trying to figure out, okay, what is different about this thing that I'm working on? What is the context of this specific circuit I'm working on in the broader context of all electronics? And then you can start to solve your problems. Now, along the way, you're going to have to, of course, apply Ohm's law, and you're going to have to go and do some math at some point. I have been accused of hating theory, but that's actually not true. You actually do need to learn this theory at some point. My assertion here is that you have to start from a broader level, a broader context, in order to really start to understand things. Because otherwise, if you start at the equation level, you start bottom up, I think you're going to get frustrated. You're going to find that you're not making the progress that you really want to. So there's another thing here that I'm not a huge fan of this term, but I think it actually does apply. This is just-in-time. So just-in-time learning is kind of a trend these days. And what it really is the same thing we all understand, right? It's Googling, it's looking things up on the internet, it's using resources that we all have, but it's actually doing so when you encounter that problem. Another thing that I see a lot of students doing is starting at the beginning and say, well, I can't put a resistor in a breadboard unless I understand all equations in electronics. And if that happens, you'll never build that dome light. You'll never build that car. You need to start building first, gathering context around it, and then when you need to, then you go dive down and start learning about Ohm's law or all the physics that you need there. Now, there's a lot of other good resources here, and I think that a lot of you will know them. One of them, of course, is expert systems like Hackaday.io, right? So the Hack Chat is a great resource. Sometimes you're not going to be able to find that piece of information you need. There isn't a Wikipedia page, or there isn't an equation that you need, or you don't even know which one to look for. And that's where systems like this, you can go and talk to people and interact and get a little bit of assistance to point you in the right direction. That's actually one of the magical things about the Hack Chat. Now, if you've done that for theory, right, you've started to understand theory, you've built one of something, you start doing that for manufacturing as well. You say, oh, well, I built one, I want to build 10, I want to build 100. That's actually another expert system we have called Supply Effects. This is the new thing we're working on. And this is actually really great for, okay, now I've built this thing, I understand how it works for one, I need to build 10, I need to build 100. And there are a whole new set of challenges there. And that's where expert system around manufacturing is really going to help you move forward in your career and maybe even make money and make new products and all this other stuff. So, in conclusion, iterating designs, going from the top down, is really going to make sure that you are understanding circuits and you don't fall off the map as you're trying to learn new things, right? Using modules, using others' designs, and iterating on those. I mean, problems are going to find you either way. It's good to start with a known quantity and then break stuff over time and fix it as you need. Also, don't dive down the rabbit hole. Start from the top, understand system level stuff, and then learn as you need to as you dive down the abstraction layers and you start to encounter new problems. Thanks.